Good morning, everyone. Myself, Ashu Sharma, Assistant Professor, Department of Computer Science and Engineering, Arya Institute of Engineering Technology and Management. Today, we will see filtering for removing noise, which is present in an image. So, in order to start this, very first is a spatial filtering for removing noise. Skills similar to image enhancements, the mean filters, the order static filters, and adaptive filters. These are such categories where we can see towards the solution for removing noise or a type of error from an image due to some technical faults and due to some processing and transporting of image from one node to other node. So arithmetic mean filter is let xy presents the set of coordinates in a rectangular subimage, window of size myn centered at x comma y. So here is the center is x comma y. The filter that computes the average value of the corrupted image in the area defined by sxy. So the filter is going to compute the average value. So here we have total number of cell 1, 2, 3, 4, 5, 6, 7, 8, 9. It means this matrix having 3 by 3 dimension, 3 rows, 3 columns. So that according to the formula, this f cap x of y is equals to f of xy equals to 1 upon mn, and that is the summation s comma t belongs to sxy gst. So we have to take sum of all the elements and then divide it by that 1 upon mn. So mn is number of m is number of rows, n is number of columns. So the multiplication of that for this, you can say this is that summation of all these values and divided it by 9 because total number of elements are 9. So this is implementation of the arithmetic mean filter implemented as simple smoothing filter, and this is well suited for Gaussian and uniform noise, as we discussed earlier that Gaussian noise is the superclass of all types of that noise models that presented an image. So that is applicable. Arithmetic mean filter is applicable for such kind of noise. Next is how to compute geometric mean filter. So each restored pixels is given by the product of the pixels in the subimage of windows, and that raised to the power 1 upon mn. So achieves smoothing if you comparable to the arithmetic mean filters, but tends to that lose lossless image details in the process, and it is also well suited for the Gaussian and uniform noise, but it achieves that smoothing comparable to that arithmetic mean. So here is a formula f cap x pi equals to that pi sc summation that is belongs to si gst and whole sum power 1 by mn. So what we do, we simply just product all the elements present in the matrix and then whole raised to power this 1 upon mn. So this is the way that we compute geometric mean filter. Now the next one is the harmonic mean filter. So it works well for the salt noise but fails for the paper noise. So when we talk about the uh, black and white type of noise, salt and paper noise, then generally we used to apply this harmonic mean filter, but it fails for salt noise. It doesn't have that better results for the paper noise. So also does well for the Gaussian noise. In the previous two filters, in arithmetic mean filter and geometric mean filter, that was working for the Gaussian and uniform noise both, but harmonic filter is working for the Gaussian noise. So here we have f cap xy equals to mn upon that summation s comma t belongs to sxy 1 upon g, and this is function of s comma t. So g of st. So what we do, we are simply putting this value like that. That mn is simply 3 into 3 as per this given matrix. This given matrix mn is 3 by 3 into 3. So it will be 9 upon 1 upon and each element's value that comes. So this way we calculate the harmonic mean filter, which works well for the salt noise, but doesn't have that proper results for the paper type of noise. So here we have one this diagram. This is the original image of that PCB circuit, and you see image corrupted by the Gaussian noise. So that clarity is not there. So after applying 3 by 3 arithmetic mean filter, that noise is removing, and after applying 3 by 3 geometric mean filter, you will see that the results are going to be proper. Now, there are order statics filters. So, these filters are also very important along with those spatial filters. That result is based on the ranking and the ordering of the pixels that contain in the image area that encompassed by the filters. So, median filter is simply that f cap xy equals to median, s comma t belongs to sxy, and g of st. So, effective for both unipolar and bipolar impulse noise, excellent set noise removal without the smoothing effects that can occur with other smoothing filters. So as we saw in geometric mean filter, there was smoothing effects that were coming, but here it is excellent at noise removal. The median filter is, and without the smoothing effects, that can occur with other smoothing filters as well. So next is the max filter. So good for the paper noise. F cap xy is you have to take just max of all the elements that is present in the matrix. According to this expression, max s comma t belongs to sxy and g of s comma t. Same is for the mean filter, good for the salt noise. So you have to take minimum value among all the values of the matrix elements and use this expression to find out the value of the mean filter. In median, generally the elements will be arranged in the sorted order, and then you have to pick the middle value in that list of the elements, and that value belongs to the median filter. So this is the way that median filter is having that sorted patterns. You have to arrange that element list in the sorted pattern, and you have to pick that middle value from there, and that's where you compute the median filter value. In the max filter, you have to just simply take the maximum value among all the elements of the matrix of the list, and in the minimum filter, you have to take the minimum value. So max value is generally for the paper noise, and the minimum filter is used for the salt noise. So this is the way. Next is the midpoint filter. So good for the Gaussian and uniform noise as well. So as we saw in spatial filters as well, that was good for the Gaussian and uniform noise both. So here is a formula. We have to simply take first the max filter and then min filter, make it sum of them, what are the values, and then divided it by 2. So this is the expression f cap xy equals to 1 upon 2. This is the max of g of st plus minimum of g of st, and then they take sum of both of these, max and min, and divided it by 2. So this way we can compute these. These are the results while passing that 3 by 3 median filter, then result of 2, then passes again median filter, and finally 3. So 3 times you are passing, and you see that effects of that, some kind of that blurriness in the image is going to be removed. So that is the effects of the median filter. Now, periodic noise reduction by frequency domain filtering. It removing periodic noise from an image involves removing a particular range of frequencies from that image. So band reject filters are there, band pass filters are there, and notch filter are there. So these are following expressions that band reject filters that removes or attenuates a band of frequencies about the origin of the Fourier transform. Then idle band reject filter, this is the expression h of uv, that is 1 if this d naught, where d naught is the radial center, and d naught minus w upon 2, here w is the width of the band, and dub is the distance of point from the origin. So if this subtraction part is greater than d of uv, then value is equals to 1. If it is greater than this d naught minus w upon 2, dub, which is distance of points from the origin, if it is greater than equals to d naught minus w by 2 or less than equals to d naught plus w by 2, then it is 0. And if dub is greater than d naught plus w by 2, then it is again 1. So this is the way this idle band reject filter works. Next one is the Butterworth band reject filters. H of UV is equals to 1 upon 1 plus dUV into W upon d square UV minus d naught square and whole power 2n. So this is the expression that we use for Butterworth band reject filters. And for the Gaussian that band reject filters, we have the formula h of uv is equals to 1 minus e raised to power minus 1 by 2 and d square uv minus d naught square upon d uv w and whole power 2. So these expressions you have to remember that directly you can apply in the exams. So this is a figure that we see that idle band reject filters. This is that Butterworth band reject filter, little bit curvature richer trajectory is there, and Gaussian band reject filters is there, so more smoother than compared to previous tools. So this is that we have from this session. Thank you very much being with us and discuss these topics, that what are different filters we apply when we talk about the spatial and order static filters while removing a kind of error or a noise patterns from an input image. Thank you.